I'm Roger Dingledine, and I'm going to be talking to you a little bit about an extension to Tor that we're working on. So the basic idea is, right now, there are lots of people all around the world, including in China, who are using Tor, and they're happily connecting to the Tor network. They're getting their anonymity, their privacy, their security, their censorship resistance, whatever they want to call it. But what would happen if various governments or corporations decided to actually filter connections to the Tor network? At that point, it doesn't matter how good Tor is, because you can't get there. You can't get whatever properties it provides. So our goal is to add a little bit of extension to that, and I'm going to talk you through what we've got now, what we need to add, how it works, stuff like that. So there's a lot of material we can talk about. Feel free to jump up and down and ask questions in the middle if I say something that totally makes no sense, because probably somebody else didn't understand it either. So I'm going to give you a crash course on Tor, talk a little bit about what the goals are and what our assumptions and threat model are, who we're actually trying to protect against, what Tor offers now, a bunch of different current solutions that are out there that we can build off of and maybe steal some really good ideas from. And then what are the actual components we have to add to Tor so that we can build a good system, and then all the other messy things that show up when we try to take the theory to the practice. Okay, so big picture for Tor. We're a free software system, freely available, open source, unencumbered by patents. You can get it and change it and give it to your friends. It comes with a full specification and full documentation. This is really great because a lot of researchers have now said, okay, I'm going to do some research on anonymity systems, and this Tor thing already says exactly how it works, so I'm going to start there. That's the thing I'm going to do my research on. It also means that a couple of other researchers around the world have built compatible Tor clients, and it turns out that we found some security bugs in our spec while they were doing that. So I heartily recommend multiple implementations if any of you are still uncertain about that. We were also chosen as the anonymity layer for the European Union's PRIME project, which is a big 30 million euro prototype how you would do privacy in online communication. And they picked us as sort of the bottom layer. Whenever you want to talk anywhere, you should use Tor, because once you have your anonymous credentials and your anonymous other things, it doesn't matter if you're broadcasting who you are while trying to do fancy crypto on top of that. So we've got some number of users. It's an anonymity system, so it's a bit hard to count exactly how many we've got. But it's somewhere on the order of a few 100,000 people are running Tor clients right now. We push a little over a gigabit per second of traffic, and we've got a capacity of somewhat higher than that. How many people in here saw Mike Perry's talk in the last session? A few hands, but not very many hands. Okay, so I'll try to give you an overview. Also, various magazines have decided that we're cool. A couple of years ago, PC World magazine picked us as number 40 out of the top 100 products. I think we beat out Wikipedia, we beat out the iPod. I think this year they've picked us as one of the top 25 products you've never heard of. So I don't know if they never looked at their previous issues of the magazine or what, but there are various magazines that keep talking about how interesting we are. Okay, so a little bit of background in terms of who cares about this stuff. One of the fun things about working on Tor is the diversity of users out there who care about it, and we try to bring all of them in to the same network. So when I talk to my parents and grandparents, I don't work on anonymity systems. Anonymity systems are sort of weird and technical. I work on privacy systems. And when I talk to businesses, Google, Walmart, stuff like that, what do you say? Never mind. When we work on businesses and Google and Walmart and stuff like that, we work on network security. We work on communication security. Because anonymity is scary again, and they don't want that privacy stuff, but they do need their communication security. And then when we talk to other organizations, maybe the Naval Research Lab or military or something like that, we work on traffic analysis resistant communication networks. And that's, again, a big word, and they don't care about their privacy or their anonymity, but boy, do they need to resist traffic analysis. So part of the fun of this is bringing all these different groups together. Some of them want their privacy, some of them want their security. You need to put them on the same network so that they can blend together. Another part of the fun of Tor is the diversity of funding that we've gotten. We've been funded by the Naval Research Lab, DARPA, the DoD, the military complex. We've also been funded by the Electronic Frontier Foundation, and more recently our funding comes from another government group, which is nearby to Voice of America and Radio Free Asia and Cuba and Europe and stuff like that. They've got some websites in the world that a lot of their users can't reach. and they'd like to fix that, and we sure wouldn't mind fixing that. So that's a little bit of what I'm talking about today. Okay, so a little crash course on how you get your anonymity. The easy answer is you put a computer up there somewhere, maybe in San Diego, and you route all of the users to it, and each user shows up and says, hey, I really want to load indiemedia.org, or hey, I really want CNN, hey, I really want Voice of America. And then the proxy, the relay, goes and gets them and hands them back. And the idea is that Bob over there doesn't know which Alice has asked for the question. So that's very straightforward. This is how most commercial anonymity systems work. Maybe you use encryption between Alice and the relay so that nobody can snoop on that. But the big problem is what happens if the big central point of failure turns into a central point of failure? Maybe you go threaten the CEO, maybe you get a job as the janitor, maybe you send them a subpoena, maybe you just walk in and take their computer. There's so many different ways that a central point of failure can fail. So the goal for Tor is we want to distribute the trust. We want to make it so that you step over several different relays, and no single relay knows about both Alice and Bob. So maybe the first relay is bad. He knows that Alice is using Tor, but he doesn't know what she's doing. Or maybe the last relay is bad, and he knows that somebody's talking to Bob, but he doesn't know who's talking to Bob. And maybe they're both bad, in which case, if you went to the earlier traffic analysis panel today, you will learn that we're probably screwed. If you're able to watch both edges of the connection, then you can do some traffic correlation attacks. You can say, hey, wait a minute, I saw a stream over here that looks like this, and I saw the same stream over here that looks like this. I'm pretty sure that these two people are talking. And since we're trying to be fast enough that you can browse the web or instant message or something like that, then we've got no defense against that. So the way that we have our security is by growing a large enough network that not very many attackers are going to be in the right places to see both the beginning and the end of the circuit. Right now we've got 1,000 servers on 5 continents. So as we grow, there will be fewer and fewer attackers who have the resources to be in the place to attack both sides of the circuit. Okay, so that's a crash course on Tor. And there's crypto and stuff to it. I'm going to skip over all of that. Yes, question? We're missing Antarctica. I don't think we've got any satellites. Africa. We had a node in South Africa every so often, but bandwidth is really expensive there. We also had a node in Namibia or something for a little while. I don't know whether they have internet there, but there was a server there. It was pretty fast for a little while. I think it was at like Kilimanjaro University or something. I don't remember where it was. Maybe Kenya. But anyway, what?
I see one node in Africa.
Oh, good.
Morocco. In Casablanca.
Morocco. Well, today there's a node in Morocco. Six continents. Excellent. Okay, and there's crypto behind it, which I'm going to skip over. Feel free to ask me afterwards. Okay, so what are we talking about today? There are a lot of different ways that you can block connections to the Tor network. The easy way is there are directory authorities that tell you who's in the network, and there are 5 of them. Users use them to bootstrap. You go fetch those 5 IP addresses, you filter them, and you're done. Or you go fetch the directory, and it's got a list of 1,000 IP addresses, and you filter those, and you're done. Or you look at the network fingerprint. You say, good thing those guys follow all the protocols, and they write in their little SSL transaction, hey, this is a Tor transaction. And then you just look for the signature that looks like that, and you block that on your IDS. So there are a lot of different ways that can be done. So our goals are to address all of those. Step 1 is try to figure out how to get a lot more relay addresses. So there aren't just 5 addresses out there that you can block. And then normalize Tor's network fingerprint. We really want to make it look like an ordinary SSL connection or Skype or something like that. We're still in the research phases in terms of which protocol we want to try to blend in with best. And then also solve the discovery problem. That's what I'm going to be talking about a lot today. How does the user in the blocked area find something to relay through? How do you get your first connection? And then the challenging part, don't screw up our anonymity properties while we're trying to do all this. Okay, so what sort of assumptions are we looking at here? Another way of looking at that is, what's our threat model? So one of the fun things about working on blocking resistance or censorship resistance is if you go back through the last 5 years at DEF CON and Black Hat, especially DEF CON, there are a lot of people trying to solve this problem, and they don't know what the heck problem they're actually trying to solve. So they sort of say, well, imagine that the attacker is a superpower with $1 billion and they really, really care. Now what do we do? And then they end up saying, well, gosh, I guess I can't do much. So we're trying to describe the situation as it is right now, and hopefully we can take advantage of that. Okay, so first step, try to defend against a pretty strong attacker. We could say, well, let's hope they don't care. And that would work for the first while, but then they might start caring, and then we'd need a better solution. So we're trying to work on that better solution here. So we've got a lot of users in mind, maybe people in Thailand, people in China, people in Indiana who can't get certain US websites. Maybe we care about whistleblowers and corporate networks, and we really want to be useful in the future also. Who knows what the next oppressive situation is going to be? It'd be nice to already handle that. And attackers are going to be in different stages of the arms race. Maybe one of them subscribes to SmartFilter. Maybe the other one has 30,000 people working very diligently at finding every bad URL on the internet. And maybe some of them are in between. Okay, so what do the attackers want to do? They want to restrict the flow of certain sorts of information. And there's sort of two classes of this. One of them is embarrassing information, human rights violations, corruption, stuff that they don't really want published about their organization. And then the other one is opposing information. Maybe somebody's trying to organize protests or movements or something, and they really want to make sure that information doesn't get out there. Or they can actually just chill the behavior by giving people the impression that they're watching what's going on. They don't actually have to go find all the people talking about rights violations and make them stop. They can just give you the impression that they're doing that, and most people will self-censor. Most people will say, well, I'm pretty sure they're watching me, so I'm not actually going to publish this thing, even though maybe I should. Another point, complete blocking is not a goal. It's not even necessary. All you have to do is find the ones that are quite popular or quite useful and shut those down, and then you can really focus on the last 7 people who are still using some sort of system. So you don't need to do complete blocking of all bad things on the internet, and you also don't have to shut down every single circumvention tool. You just have to focus on the ones that are popular and effective, the ones that work, have lots of users, and the ones that are highly visible. If they have New York Times articles coming out every week saying, such and such project declares war on China, then China's going to notice and they're going to have to react, not because it matters, not because they actually have to block it, but because they need to have the appearance that they're blocking it. Okay, another question, maybe some goals they have. An assumption that we've been making from talking to a lot of people there, if you're just reading something on the internet and you happen to get through the firewall, for example, they didn't filter it yet, then that doesn't matter. They're going to say, oopsie, and they're going to add that URL to the firewall. That's all that happens in practice. On the other hand, if you're publishing things that they don't want you to publish, then they are going to look a lot closer. They're going to try to track you down and figure out what else you're doing and try to discourage you from doing that. And then another assumption we might make, censors have economic, political, social incentives not to block the whole internet. This is a big question every time we ponder censorship systems. If we force a government to unplug their whole internet connection, did we succeed or did we fail? If we take the arms race that far, is that a success or a failure? And in our case, the assumption is that they're not going to do that. They're not going to be willing just to shut off the whole internet. And that's true in a lot of countries, and it's not true in others. In Burma, for example, I think you can be arrested for owning a modem. So that's going to be a tricky situation for us to tackle. But in some cases, that works fine. And also, they don't want to turn the whole internet off, but they don't mind a lot of collateral damage. Maybe there's a blogspot thing that they really don't like. So they turn off all 20,000 blog spots. They don't mind, hey, they're just blogs, whatever. Okay, so there are a couple of different attacks that we've actually seen in the wild from these filtering or censorship systems. Probably the big 3 are they have a list of IP addresses and ports that they try to block, and they do keyword searching in TCP packets. So if you have democracy or Falun or something like that, then they look for these little substrings, and as soon as they see a TCP packet with that substring, then they send reset packets in both directions and try to break the connection. And then also they intercept DNS requests and they send you to a different page. And that page says, hey, it looks like you're trying to access censored material. I think you might be a bad person. Maybe you should consider reforming, or whatever the page happens to say. And that tends to work also. Okay, so a lot of design assumptions that we want to think about here. One of them is the network firewall has limited CPU and memory per connection. It's not like you can sit down and say, okay, let's do some statistical analysis and let's try to break the crypto here and make sure that you're obeying the protocol perfectly for every single person in one of these countries connecting out. All they can do is look at it in a cursory way and say, okay, that kind of looks like SSL, or hey, look, I know where that connection's going to, I'm going to block it. So we don't need full steganography, which is useful because I think it's impossible. But that's also something we can get into afterwards. And also, we might assume that there's a time lag between attackers sharing notes. Maybe a certain country figures out how to filter some system, but the next countries don't figure it out for quite a while afterwards. And then maybe the exception to that is a company like Cisco, where they say, we have developed a new innovation. This new tool will let you oppress your citizens better, and we're going to sell it to every country who wants to buy it. So that's maybe one of the vectors for how these sorts of attacks that we might worry about would spread. And then another point, insider threat is not a worry when we start. If we build up a network with a bunch of volunteers who are helping people relay around, we're not going to have a huge government infiltrating the network and signing up half the volunteers at the beginning before anybody knows about it, before it is useful or visible. Okay, and then censorship is not uniform inside these countries. If you talk to a lot of people in China is the example I've been using, but there are lots of other ones. There are a lot of different ISPs, and each ISP, it's not like the government at the very top says, you will filter the following 47,000 places. They send down a very loose set of instructions. They basically say, don't embarrass us. And every poor guy at each ISP is left to say, well, what does that mean? What am I supposed to filter to not embarrass you? So each of them have to say, well, I guess probably not porn, and I guess probably not webcomics, and I guess probably not. And so each ISP ends up with a different set of things that they think they'd better filter. And that makes it a bit challenging to actually measure things. A lot of people say, well, what does the Great Firewall of China block? And at that point, the answer is, well, if you're in this province, it blocks this and this, and actually tomorrow it's going to block this because some guy thought it was a good idea, but the next day he'll change his mind and it won't block that anymore. So that's a bit challenging. Okay, another assumption we need to make, assume that the users aren't actually attacked by their hardware and software. There's no spyware installed, no cameras watching their screens, stuff like that. And that's a pretty challenging assumption depending on the country. I was talking to a group of dissidents from an East Asian communist country a while ago. And I was there to teach them all about security, and I was all set to say, 128-bit crypto good, 40-bit crypto not so good, let me tell you how these things work. And they were getting phone calls saying, so-and-so just got arrested. And they turned to me and said, our guy just got arrested, what do we do? And then I realized that I didn't need to teach them about security. They need some basic operational security. And that's maybe at a level that I'm not the best one for them to be talking to. They were explaining that, yes, Tor would be a fine solution, but when I go to the bathroom, somebody walks into my house and answers my Skype phone calls. There's a guy across the street with a parabolic microphone listening to every word I say on Skype. They steal my laptop and install stuff on it and give it back. That's a bad situation. I'm not trying to solve that one here. Maybe we'll get to that eventually. And then, similar to that, assume they can get a real copy of Tor. If Burma distributes the Burma version of Tor, and you go get that one instead and you install it, and it gives you away every time you do something, you never used my software in the first place, nothing I can do to help you. So maybe PGP signatures. I've got business cards up here that have the PGP key that signs the Tor source code. So at least you guys will know you're using the right Tor. But does that really help somebody in Uzbekistan that I've never met? Okay, so those are a bunch of assumptions and pieces of the threat model to try to give you some intuition about what we're talking about. So what do we have now? Tor gives sort of three different anonymity properties. The first one is somebody watching your local network can't figure out or influence what you're doing. They can't say, Alice is connecting to CNN. I'm gonna react on that somehow. And that's clearly useful for blocking resistance. Another one is no single router in the path knows about both you and where you're going. And that means that the attacker is not as likely or as incented to sign up a couple of servers so that they can start linking users to where they're going. If we were just using a single hop proxy, then the attacker should really show up and say, well, I'm going to sign up half your network, and I'm going to learn all about the Alices who use it and all about the Bobs that they visit. That would be bad. And then the third anonymity property we aim for is the destination or somebody at the destination can't figure out where you're coming from. And that's maybe not as obviously useful, but it also means that they can't bust you. A little while ago, Yahoo, so the Chinese government went up to Yahoo and said, hey, there's this guy who's writing about stuff, and we'd like to know who he is. And Yahoo said, why, certainly. Here's his IP address. Here's his identity. Here's his mail. Here's everything that you might want to know about him. That's a shame. We'd like to sort of build a system that doesn't make that quite as easy. And then the other side of that, maybe they'll treat you differently. Maybe China goes to Google and says, anybody who's coming from China, even if they're going through this censorship system, please censor them for us, because otherwise we won't like you as much. We won't let you do business in our country, stuff like that. So there are a bunch of other things that Tor gives us right now, and I'm going to give you a brief overview of the ones that matter for the design I'm going to talk about later. One of them is we have a well-analyzed, well-understood discovery mechanism. We've got these things called directory authorities. There are 5 of them. Their locations and their public keys are hard-coded in the Tor that you get, so you know you're bootstrapping into the right network. They automatically aggregate all the Tor servers out there. They test them to see if they're up. They publish signed summaries of all the servers you might want to use. Clients go to either the authorities or any mirror, and they fetch a big list, and now they know who they can use. And this is important for anonymity reasons, that the clients get the same list. You don't want to have, well, I used this 40% and I used that 20%. You want all the users making the same sorts of decisions over the same sorts of input, or they're not going to blend together very well. Okay, so that's piece 1. Piece 2, the list of directory authorities, there are 5 that are put in by default, but it's not like they're hardwired. You can put in your own default. You can go to the configuration file and say, I don't want to use those ones that the Tor guys want. Here's my new set of directory authorities. And suddenly you're connecting, you have created a new Tor network. And that might be handy for all sorts of reasons. Maybe somebody could set up a separate Tor network in Iran or in Indiana or whatever sort of situation they might need one. On the other hand, you really don't want to have 50 different Tor networks out there, because then you're splitting your users up between a lot of different networks, which again is bad for anonymity. Okay, what else do we get? Tor automatically builds circuits. They're called paths. And it rebuilds them and rotates them, and it takes care of making sure that you've got a circuit up and available that will support whatever connection you want to do. So more broadly, Tor is just, it's a tool. You put in a bunch of server descriptors, and it builds paths through them. So you could get your description of what servers are around from the directory authorities, or you could get them some other way. We don't care. You tell us about servers, we build paths through them. I've been talking with a lot of community wireless people because we've got a tool that lets you build paths through whatever network you happen to have. And they provide TLS for free, and it's pretty easy to extend. So we're not just an anonymity system for the Tor network we happen to have built. We're more of a general purpose tool. And Harvard's project called Blossom makes this a little bit more concrete. They don't care about the anonymity properties of Tor. They care about the reachability properties. They want to say things like, show me CNN.com from Iceland, or show me the resource called the website from the location called Jeff's apartment. And at that point, Blossom will automatically build a circuit that ends at wherever you want to end, and it'll go to that resource. So this is another way of being able to look at the internet from different perspectives and get a better sense of how people in various areas of the world can see things. Okay, another feature, Tor separates the role of internal relay from the role of exit relay. So Tor servers have these things called exit policies. They specify which IP addresses and ports you're willing to connect out to. Some people say, I'll connect to anything. Some people say, my IT guy already hates me. I'm going to be a non-exit node, so he doesn't hate me anymore. And it depends a lot on what you want. So this means that we can have a lot more servers out there than we would if we demanded that every single server be an exit node. Okay, so this increased diversity is sort of where Tor gets its security, its anonymity, because having a lot more servers, as I described at the beginning of the talk, that's where our security comes from. The larger the Tor network is, the more diverse the servers are, the more likely it is that there is not an attacker who can be on both edges of the network. Okay, another feature, Tor is sustainable. We've got a community of developers and volunteers. They help out. They do all sorts of things. There's a question in the back. Yes?
Is there a ratio of exit relays to internal relays?
Is there... Yeah, so the question is, do you have enough exit relays, or do you have 5% exit relays and 95% internal relays? And the answer is we have about a third exit relays, which is about the right number because for 3 hops you want about a third of them to be exits. We'd rather have more, of course, because right now, since about a third of them are exits, we have to not choose the exit servers anywhere else in the path or we're going to overload them. We're going to put more than a third of the traffic on them. So it would be great to have more exit nodes because then we'd end up having more possibilities for every choice, and that leads to more anonymity. Okay, so one of the interesting things about the anonymity world is periodically people say, I'm going to make money off this. I'm going to build an anonymity system, probably using a one-hop system, and I'm going to charge users to use it. And then we'll all get rich. They'll have their anonymity, I'll have a big startup. Typically, you don't collect enough money from these users in order to actually pay for your bandwidth, and it all goes bad. So we're more of a volunteer community effort where various people around the world say, I've got some extra bandwidth, this is important, I think privacy, security, anonymity, whatever you want to call it, is important, so I'm going to donate to the network. So our sustainability is rooted in the open design, the clear specification, modularity, open source. This means that we're more likely to be around later on as a tool that could be used for whatever people want to build out of an overlay network. Okay, and we've got a few 100,000 users all around the world. Ordinary citizens, activists, corporations, law enforcement, government, military. There's a group of Navy soldiers in the Middle East right now who are using Tor to connect back to their mail servers in Maryland. And they don't want anonymity. They really do want to authenticate to the mail servers in Maryland, but they want protection against an eavesdropper. They don't want somebody watching the house in Iraq to say, hey, I know what their affiliation is. And they don't want somebody watching the mail server in Maryland saying, hey, I know what their current location is. So that's a separate talk of what the sort of uses for Tor are and who cares about it. But the diversity of users contributes to its sustainability. It means that if somebody starts to pressure the Congress or whatever to make laws against security or anonymity or privacy or whichever way you're phrasing it, then we're going to have a lot of different people talking to them saying, hey, wait a minute, you can't take away my business security. I use that to look at my competition without them knowing what I'm doing. So that's one thing. That big pile of users also gives us a whole lot of IP addresses. And I'm going to make use of that in a few slides. Okay, and also anonymity is useful for censorship resistance. We talk to a lot of people who say, well, just ask your uncle to put up a relay. Maybe you're in China, you're at some factory, you want to tell about some problem at the factory. So maybe your uncle moved out of China and he lives in Ohio, and ask him to put up a computer, and then you can connect through that and you can post. That sounds great, except there are a couple of problems. One of them is, so I guess there are several issues. One of them is then somebody watching that relay can figure out, oh, hey, wait a minute, she communicated through that to the blog site. But maybe a worse one is if you look at the blog site and you say, hey, that thing that I wanted to censor, it came from this IP address. Hey, the guy who owns that IP address is the uncle of one of the factory workers, you can sort of trace back pretty straightforwardly and say, now I don't know for sure who posted this, but whoever did it knows this person, and now I'm going to start making some correlations pretty quickly. Or they can just spread suspicion that they're doing this sort of attack, and maybe people won't even do that in the first place. Okay, so that's a little bit. I'm halfway through. I've gone 30 minutes. Okay, great. Okay, so that's what Tor offers now, and I'm going to talk a little bit about the deployed solutions right now, and we'll sort of take what we like best out of them and go from there. So one of the important points here is there's sort of two components to these circumvention tools. One of them is called the relay component, one of them is called the discovery component. And we can break them down and look at them separately. So the relay component is, how do I actually build the paths through the servers? How do I actually do the crypto so I get it right? And then the discovery component is, how do I find that first thing that I want to connect to? How do I find some relay so I can get to the Tor network? Or whatever network we're talking about. In the case of Tor, this is pretty straightforward. We've mostly focused on the relay component. How do we actually build the paths right? And then we just tacked on a discovery component at the end. We said, okay, we need a way of finding the servers. Let's build directory servers, and we'll just use those two things. But the key point is that these are sort of separate ideas. How you do relaying once you know about servers, and how you learn about servers can be developed separately, and you can mix and match. Okay, so there are a couple of different schemes out there. On the one hand, we've got centrally controlled shared proxies. These are maybe big central commercial anonymizers. They've got a bunch of single-hop proxies all around the world. They control and operate most of the proxies centrally from some big company, or maybe they hire a lot of people, and in their contract they write, please don't collude with anybody else who's in this contract. And the goal is a lot of different users get centralized in each one of these proxies. And they hope there's some anonymity there. That's sort of an open research question too, but it's not very promising. So these one-hop centralized proxies have weak security compared to a distributed trust design like Tor, because there's that one point of failure, you go to it, and now you win for all of the users using that. But they're really easy to deploy. You just put a proxy out there, and then you can even do it through the web, through a web browsing interface. You don't even have to install software on Alice's side. You just say, go visit that URL, and it'll take care of anonymizing you. So it's really easy to use, but we need to keep in mind that the reason why users don't need any new software is because they totally trust the proxy already, so what's the point? So that's something we can start with. On the other end of the spectrum, rather than something that aggregates a lot of users into a single place, imagine independent personal proxies, systems like Circumventor or CGI Proxy or Siphon. So they've got the same relay strategy. The relay strategy is easy. It's, I put a proxy out there and you proxy through it. There isn't much more to it than that. But the discovery component is different. In the first case, the discovery component was, hey, there's a URL and everybody uses it. That seems kind of easy to block. In this case, the new discovery strategy is find a friend to install it for you. I hope you have an uncle in Ohio or something like that. So this is great for blocking resistance. Nobody is ever going to notice that computer out there has one guy relaying through it every so often. If their goal is to find the top 10 IP addresses that dissidents use, that's never going to be on the list. On the other hand, there's a huge scalability question. How does the guy in China find the volunteer in Ohio if they don't happen to already have a relative there? And then the flip side of that is, let's imagine you're in Ohio and you really want to help out. How do you find a dissident who needs to proxy stuff through you? How do you actually get hooked up? So that's another building block we can use. Open proxies. Google for open proxy list. I don't need to tell the Black Hat audience about this. There are plenty of them out there. There are even companies in Russia that sell refined lists. They guarantee 30 kilobytes or better of bandwidth. They guarantee up. Who knows what else they guarantee in terms of operated by the Russian mafia. But these are out there, and there may be a tool that we can use also. Okay, so there's another system called the Java Anon Proxy. It's built by the research group at Dresden. And it's a similar anonymity tool to Tor. There are a couple of differences in terms of what level of anonymity that they can provide and we can provide, but that's also a separate talk. So they have a similar idea to what I'm going to talk to you about in a bit. So their relay component, I'm going to skip over, but the discovery component they describe is a CAPTCHA. It's a little picture, it's got some letters in it, and they say, hey, tell me what's in the letters. And the idea is there's a rate limiting going on where they give you the little picture, and you have to prove that you put a little bit of effort in, and then they give you an address. And as long as they've got enough addresses that the attacker isn't able to fill out CAPTCHAs quickly enough, then they're in business. Also not perfect, but it's something we can build off of. And then we've got Skype. It does port switching, it does encryption. It's a little bit hard to block. It still has a central login server, so it's not perfect. But they've got a lot of tools that we might be able to make use of. They look like SSL. They try to move around and find which ports aren't firewalled. And then there's Tor itself. Tor's website is blocked in a lot of places. It's blocked in Iran. It's blocked by the LA Times. I was talking to a reporter earlier, and they really wanted to do a story about Tor, except they couldn't read the Tor website because whatever proxy program they used to filter their corporate internet wouldn't let them read about Tor because it was scary. So the Tor website is blocked in a lot of places, but the Tor network is blocked in almost no places. So why is that? I mean, aren't we a circumvention tool already? Aren't there tens of thousands of people who are using it right now to get around their government firewalls? So there are a couple of speculations. I mean, the easy answer is, gosh, I don't know. Why don't we ask them? But they haven't told me. So one speculation is, sure, there are 30,000 people in China using Tor. So what? 30,000 is zero. They've got a lot of people there. Nobody cares. That could be. Another answer is that the perception that we've been giving out so far is Tor is for experts. If you want to set up your Tor right, you need to be able to edit a file. And right there, I just shed 99% of the users that we might have. And as long as we continue to sort of work in that paradigm, again, nobody's going to care. And then another perception, another possibility, nobody has publicly threatened their control. As long as we keep talking about how useful Tor is for civil liberties and for the law enforcement and military and companies and so on, then we're not going up there and saying, hey, this is a big deal about human rights. And as long as we're considered to be a free speech tool, then we're not a human rights tool and they don't care. More importantly, the folks who are building the block lists and the folks who are wondering what they should block don't consider this a threat. But I guess the key point is we're already in the arms race. For all those people who say these attackers are super powerful and super dedicated and they'll block everything and they'll make sure to look inside all the steganography, they don't. It's working. So, I mean, it's not going to keep working forever, but we're already in the arms race and we've taken several steps, so we should learn a little bit more about that and maybe we can make use of that also. And we can learn a little bit about the priorities and the constraints of the various attackers that we've got right now. Okay, so that's a little bit more about that. So what do we need to add to Tor? What are we going to what components are we going to try to build in order to build a system like this? So the first point is we've got a lot of users. What would happen out of these hundreds of thousands of users, and they're already self-selected for caring about privacy, what would happen if we took the Tor GUI called Vidalia and we put a little button in it that says Tor for Freedom? And when you click the button, then you turn into a relay. You don't volunteer to be a server in the main network. You don't publish to the main directory authorities, but you publish somewhere else. And you rate limit to 20 kilobytes a second, which is nothing for somebody on cable modem, but it's a whole lot for somebody on a modem in Iran. And these can be internal relays. They don't have to be exit nodes. They're just bridging from the blocked area to Alice to the Tor network. So Alice, in this case, is the bridge. She's going to be an ordinary Tor user. She does her own Tor stuff, but she clicks the button, and now maybe some blocked user can relay through her into the Tor network. So the idea is maybe if we've got a few 100,000 of these Alices and maybe 10% or 20% of them end up clicking the button, now we've got a lot of IP addresses to work with. And maybe we can do something smart with those in terms of the discovery strategy. Okay, so once we've got these bridge relays, we also want to add a new concept called bridge directory authorities. You run a bridge relay and you publish yourself to the bridge directory authority or the bridge authority. And that way it can aggregate a bunch of different volunteers who said, yeah, I'm okay with people relaying through me. I'd like to, Tor for freedom. Yes, good. And at that point, the key difference between these directory authorities and the main ones is we don't give out a big list. The main directory authorities say, there are 1,000 servers and here they are. And you can also do individual updates. You can say, I know about a server with this identity key. Can you please tell me his newest descriptor? And the descriptor includes current IP address, keys, exit policies, stuff like that. So the idea is for these bridge authorities, you can, if you already know the identity key of your bridge, you can query the bridge authority and say, hey, where did you move now? But if you don't know the identity key already, then there's no way for you to learn the whole list. And I'll talk a little bit more about how all of that works in a bit. But then I guess the other point is the identity key and the address for the bridge authorities should ship with Tor along with the main bridge authorities. And also bridges should publish to the authority using Tor. Otherwise somebody should just watch the bridge authority's network and they'll learn about all the bridges as they show up and sign up. But if you use Tor, then there's no central place to watch to see who has volunteered. Once we have an anonymity system, we can use it for all sorts of things inside the anonymity system. Okay, so another key point here. Once you've got one bridge, we're good enough. Once you've bootstrapped to the point that there is some bridge out there that you can use to get to the rest of the network, then we've gotten past the hard part. And at that point, you can use that bridge to connect to the Tor network, to connect to the directory authorities, to connect to Voice of America or Indie Media or whatever pages you want to do. Once you've got one bridge working, then we're done. Then we've solved the discovery problem, and you can continue to bootstrap from there. And all of this happens in the background. So once you've got one, then Tor will just automatically take care of building the circuits for you and take it from there. So we've changed the problem from the situation they're in now, which is how do I circumvent my firewall for every single transaction and trust that I'm actually getting the right pages back rather than a page that says, it seems that you're looking at a page you shouldn't look at. Have you considered reforming your morale or your morals? So we've changed it from that problem, how do you circumvent for every page, to how do we learn about a working bridge? How do we circumvent the firewall once, and then we can figure out a bridge, and from there we can use that bridge from then on and have an automated anonymity circumvention system. Okay, and I'll get back to details of how we learn that first bridge. But a brief interlude, which I'm going to mostly skip over, hiding Tor's network fingerprint. So right now we do two protocols on the wire. One of them is HTTP for fetching new directory updates, and the other one is HTTPS or SSL for actually connecting between two Tor servers. So the HTTP one is a really bad move in terms of being filterable, because we go to a certain place and we say get/tor/server/something or other. And for all those people out there who are good at filtering URLs, you can guess how easy that is to filter. And quite a number of different proxy filtering tools have gone ahead and done that as a feature for keeping Tor users off their network. So that's step one. We need to get rid of HTTP, and we've already done that for the most part. Basically, the way it works is if I want to fetch a directory from some mirror, I'm going to do a Tor connection to that mirror, and then inside that Tor connection, I'm going to do a fetch. I'm going to ask for the directory. So in fact, Tor still thinks of it as HTTP, but it's tunneled over the TLS connection we've already got. So that leaves us with one question of how do we do this TLS connection in a way that nobody minds, in a way that it doesn't look any different from any other web connection. And the first answer is don't put it on port 9001, which is the default. Make it default to port 443. And now you really do look like a web server. And then make the TLS handshake look more like actually talking to a web server. And then the really hard part of this is when I talk to my bank using SSL, I sort of send a few packets back and forth, and then I click and I send some stuff, and then it sends stuff to me, and then I hang up. That's not what a long-term Tor connection looks like. A long-term Tor connection looks like whatever protocol you're doing inside of it. So if we get to the point where our attackers are actually looking at every SSL connection and saying, that one looks fishy, it's been going on for a long time, and they keep sending stuff back and forth, then we're back to an arms race that's going to be a bit tough. On the other hand, since a lot of people use keep alives and stuff inside their SSL connections to their bank, then maybe we've got a chance. But I'm going to skip over most of this. Feel free to ask me about it later on. Okay, so we talked about the relay component so far. The bridge relays are what we need to change about Tor's relay component in order to actually add some blocking resistance. Now let's think about a better discovery component. The discovery component for Tor right now is there are 5 directory authorities out there and you go talk to one. That's not so good for blocking resistance. So the great thing about Tor's design is that it's modular. You can take the relay component and the discovery component and you can build different ones and mix and match. So we can use any discovery component we want. That's great, except there aren't any perfect ones. It's always going to be an arms race. But at least from the previous slide, we've changed the problem from how do I keep 1,000 public IP addresses out of the hands of the Chinese government, which seems like an impossible problem, to now I have 40,000 IP addresses. How do I give them out one at a time without letting the bad guys learn all of them? And that's also a challenging problem, but it's a little bit more manageable. It's an arms race that I'm hoping I can actually handle. So the first question is, how do you bootstrap the first time? You gotta be able to talk to something the first time, because whatever that something is, they're gonna block it and then you lose. So our answer is, I hope you can bootstrap. Users are already getting around the firewall in all sorts of ways. You can SSH through most of these firewalls. You can find an open proxy, instant messaging. There are whole communities of people who SMS themselves, their friends. Hey, I found a new proxy. This is the one. There are people who use Skype, voice, and data. There's a whole community in World of Warcraft of people. They don't actually play the game. They just connect and sit around talking about new proxy servers they've found. So there are a lot of communities already for people who know how to get around the firewall, and we're going to leverage that just for the first step, just until you get your first bridge. They know how to get around it better than I do for whatever situation they're in, and hopefully that'll be the first step. And if they don't know how to do it, I hope they know a friend who knows how to do it. And if they don't have any friends, then maybe they should get some. Okay, so step 1 for discovery. No central point. It's a bunch of different, totally independent running bridges. It's like CGI proxy, which is a little CGI you can put up on your website and then tell your friends to use it. So the idea is some guy sets it up, and then he tells his friends about it. You can learn about it by knowing the bridge's operator, or maybe you know about it because there's somebody down the street who's using it, and you go down and you say, hey, I really need a bridge. I hope you know some. Can I learn one of yours? And the telling a friend part has some interesting incentives. The first one is, if you ask me for a bridge and I give it to you and you get it blocked, I can't use it anymore. So I really need to exercise a bit of discretion in who I tell about the bridges I know, or they're going to stop working. So that's a good incentive that we'd like. The bad part of it is you're mapping your social network for the attacker. Let's imagine that the attacker knows about some guy that they're really uncertain about, and they watch all of his connections and they learn about this bridge, and they say, oh, well, he has a bridge. And then they watch the bridge for a while, and they find 17 other people who are using that same bridge. And if the bridge knowledge was distributed by social network, then they can say, I didn't know those 18 people were friends. So that's a worry that I'm really not sure I want to use this technique in all situations. But it's a start. So this is one way that we can do discovery. And then another point is families of bridges. Rather than just having one individual bridge, let's have, maybe I run 30 different bridges. Or the Linux users group in Las Vegas each runs one bridge, and they're put into one set of them. So the idea is that some of these bridges will always be available. Maybe there are 30 of them total, and maybe 10 or 20 of them will be available at any given time. Because the problem with this previous design, the independent bridge, is this guy's on Comcast somewhere, and he gets a new IP address. As far as you can tell, he's gone. Your bridge just disappeared. Now you have to use Skype or make a phone call or go back to World of Warcraft and say, so where did this guy go? Where is my bridge now? If you're using families of bridges and you've got like 30 of them, then as long as one of them is still working, then you can go back and connect to the rest, to that one or the rest of them and say, so I'm pretty sure there are 30, and I bet 20 of them have changed their IP addresses. Where are the new ones? And all of this, again, can happen automated in the background by Tor. It can say, okay, so there are 30, and there are only 3 that are left reachable. Now it's time to rebootstrap before I get cut off completely. So that's another approach that we can use. And that's probably a pretty good one. It's pretty easy to write, and it's very hard to block because nobody's going to actually keep track of that many. But let's turn it around. So what about bridges who don't know any users? And what about users who don't know any bridges? Is there some way we can allow people to volunteer without having to actually know the people who are going to be trying to relay through them? And the answer is yes, we hope. It's going to be an arms race, but I'll try to talk you through the first few steps of it. So the idea is we divide bridges based on their identity key. So all the bridges show up. There are maybe 40,000 of them, and each of them has a different identity key. We want to break them up into different pools, and each pool has a different distribution strategy, a different scarce resource that we try to make the attacker prove that he has or expended in order to learn a bridge from that pool. So the idea is that each of these strategies is different, and hopefully some of them will work. And I'll talk you through a couple of them so you know what I mean by distribution strategies. So the first one is sort of a time release thing. Between noon and 1, if you show up, we give you an answer, we give you a bridge address from this subset of the pool. And between 1 p.m. and 2 p.m., if you show up, we give it from this subset of the pool. So this means that whenever Alice shows up and says, hey, I need a bridge address, she's going to get some answer. But if the attacker wants to learn every single address in the pool, he's going to have to show up between noon and 1, and then again between 1 and 2, and then again between 2 and 3, and so on. So the ordinary user gets one answer whenever she wants, but the attacker needs to work for a long time in order to learn all of them. And it's not perfect. I hear that certain adversaries can employ people, but it'll be a start, and until it gets blocked, it'll be the really easy way to get bootstrapped. You had a question? Okay, so the question is, what's to stop the attacker from blocking the bridge authority so you can't actually get there and learn more things? So the answer is, we assume that you have bootstrapped. Once you've bootstrapped and you've got one bridge, then you can go back to the authority and you can talk to them all you like. And if you ever get to the point where you've lost all of your bridges, then I'm sorry, you have to go back and bootstrap. You have to go find another bridge, however you got around the firewall before. But once you can get around it that one time, then you can talk to the bridge authority, you can talk to the main Tor authorities, you can talk to the main Tor network, then you're in business. So it's a chicken and egg thing, but they've already solved the fact that they know how to get around their firewall. We just make it so they have to do whatever they're doing once, and now we take it from there and it's automated until they lose track of bridges and then they have to go do it again. Yes?
I have a similar question. What prevents the attacker from advertising himself as a breach? And they can take over, say, 1% of the whole Tor network. They can quickly figure out who uses Tor.
Yep. Okay, so the question is, what happens if the attacker volunteers a bridge? What happens if he says, oh, use me, use me? So the first answer is, Tor is a distributed trust network. So yes, he owns the bridge, but he also has to own the other side, or he doesn't totally win. Unfortunately, it's more complex than that, and there are a number of attacks that we do have to worry about. So the easy answer is, let's hope he doesn't do that. And in a few slides, we'll get to some more complex answers. Okay, so strategy number 1 is time release. That's not going to work very well, but it's at least an intuition about the sort of scarce resources we're thinking about. Another one is by IP address or network. You publish different answers depending on what IP address the requester is coming from. If they're coming from this network, then they get something from this subset. If they're coming from this network, they get something from this subset. So the idea, again, is whenever Alice shows up, there is an answer for her, whatever that answer is. But if the attacker wants to learn every answer, then he has to show up from a lot of different places around the network. And then strategy 3 is combine them. I look at what time it is, and I look at your IP address, and there's a deterministic answer. There's one bridge that's for you. And if you ask again during that same time slot, you get that same answer. So this means that wherever Alice is coming from and whatever time it is, there's an answer she's going to get. But if the attacker wants to learn every single answer, he has to be in a lot of different places on the internet at a lot of different times. So that's one strategy, and I don't really know how well it will work, but it seems like it might work pretty well, especially because we're already taking extra steps in the arms race. We'll find out. Another strategy is Circumventor has a trick called a mailing list. You sign up on the mailing list, they send you new bridge addresses every so often. And empirically, China blocks the addresses they send out every 3 days or so. So every 3 days they send out a new mail. It's hard to say how well this will scale. Maybe somebody would catch on and they would start blocking them every 2 days rather than 3. And then they become really popular and they start blocking them every 1 day rather than 2. I don't have any idea how quickly and how well they can start reacting to this. Maybe they'll block it within 30 seconds of sending the mail. Maybe the best they can do is 40 minutes. And at that point, you've gotten your bridge, you've bootstrapped, and maybe you've learned a few more. So that's another approach we might use. It might not be perfect, but it might work. Gosh, I don't know. Or send us an email, and we'll tell you a bridge address. And we don't want to let you send a lot of emails, so we only answer once per email you send. And we want to do some sort of rate limiting, so let's implement a CAPTCHA. So you have to fill out what's in the little form, in the little picture, what letters you see. Otherwise, we don't give you an answer. And I don't want to build CAPTCHAs, so let's leave it to those great engineers at Google and Yahoo. They already rate limit for you creating new email addresses. So we only answer questions from Google and Yahoo, and we'll leave it to them to figure out how to make it hard to create 1,000 Google Gmail accounts or 1,000 Yahoo accounts. I don't know if this will work, but it's certainly worth a try. Distribution strategy number 6, just to give you an idea of how complex this could be if we want to make it complex. A social network reputation system. So the idea is we pick some seeds, pick 12 people in the country that we really trust, and give them each 100 bridges and give them some delegation tokens. And the idea is that we run a database somewhere near the bridge authority, and you can show up with a delegation token and get a new account. And this means that people who are performing well, we tell them about new bridges. And people who are not performing well, for example, everything we've told them keeps getting blocked, we don't give them new bridges. Or if we want to be a bit more sneaky, we do give them bridges, but they're bridges we already know are blocked. So they can't tell if we're actually treating them poorly or not. We just keep giving them the same answer, and it turns out that they seem to have all the bridges. I guess I'm done. Or we give them new ones, depending on whether we like them. So this gets really messy really quickly, and I don't actually think we should build this one, but it's a fun research question to start to think about how do we do a social network and do some sort of proof of work or proof of resource on the attacker's side that we can get around. And then there are a few more distribution strategies which we hold in reserve. We really want a pile of IP addresses that we haven't given out to anybody and that there's no way for the attacker to learn yet. Because what happens if the attacker says, okay, I'm going to work really hard this weekend and I'm going to block 1 through 6. I'm just going to clear them out and learn every bridge address in the list. And at that point, they're going to put out a little press release saying, that Tor thing, we took care of it. Doesn't work anymore. If that happens, and we've got no extra bridge addresses up our sleeve, then we have to, even if we've got a great new idea, there aren't any new IP addresses that we can use to fuel that great new idea. So we keep these piles in reserve, and hopefully we will never need to use them on 24 hours warning, but maybe. And then my question for you, what other strategies should we use? What other approaches could we use to make the attacker prove scarcity of some resource? One answer is SMS messages. You SMS a request to us and we send you a bridge address, but we only do it once per phone number. Google did this for a little while, maybe. Another answer somebody has suggested is encrypt it with a 40-bit key and then give out the blob to anybody who asks. Give a different blob each time. And then you can brute force it, and after a while you'll open it up and you'll see a bridge address. And maybe an attacker doesn't want to brute force 50,000 of them, but maybe Alice is willing to brute force one of them over the course of 2 days. What other strategies are there that I can use? Hopefully you'll come up to me afterwards and tell me. So one of the great things about this is we should deploy all of these at once. I don't know which one's going to work. Finally, I'm not in the position of the defender. I've got all these researchers working on Tor who say, here's an attack, you didn't think of that one. I have to defend against every single attack in Tor. But in this case, I'm on the offense. I just have to find one of these strategies that works, and then all of our users win. Whereas the adversary has to look at every one of them and say, okay, I don't know how much it's going to cost to defend against that one or that one or that one. How do I divide my resources so I make sure to beat every one of them? So the key is, by deploying all of them at once, we make all of them more likely to succeed because the attacker doesn't know which one he should focus on. Okay, so that was a little bit about what we need to add to Tor. That's the easy stuff. That's the high-level picture of how it ought to work. Now let's think about some of the messier stuff. For example, how do we figure out if a bridge has been blocked? And maybe that's related to the how do we figure out if the adversary signed one up question. So one answer is active testing via users. You've got a bunch of Tor users out there. Some of them are in China, Iran, Burma, Indiana, wherever they happen to be blocked. And you build a Tor circuit to them, and then from them to the bridge and back. And if it works, great, the bridge is working. And if you can't build the circuit to the bridge, that means that the bridge has been blocked inside that country. And if we pick random users to test from, that gets messy because then the adversary should sign up a bunch of users and say, ooh, test using me, test using me. And then they can learn all the bridges they want to. And even if we have trusted users, the adversary is still going to catch on after a while. And he's going to say, that guy over there keeps trying to connect to all sorts of places. And hey, those are all Tor bridges he's trying to connect to. I should monitor him and learn about everything he's trying to connect to. Another approach would be passive testing. Maybe the bridges themselves should keep a GeoIP database. And every 24 hours, they build an aggregate list. In the past day, I've seen 17,000 connections from China, I've seen 14,000 connections from Iran, and I've seen 0 connections from Uzbekistan. And then we can look at it, and if the graph is sort of going along normal, then that's great. And if the graph is high and then suddenly goes to 0, maybe we'll learn something from that. Or maybe we've got 7 users in a given country, and they didn't bother logging in today. Does that mean that the country started to block the bridge, or does it just mean that it was a blip? Hard to know how the stats will work on that. And then it gets also more messy. You can't just say, is this bridge blocked from China, because there are a lot of different pieces in China, and I don't really want to go mapping out the ISP infrastructure in China. And there are a lot of different possible locations for the fault, maybe at the bridge, maybe at the user, maybe somewhere between. Do I really want to start debugging the internet infrastructure in these countries just to figure out whether the bridges are getting blocked or where they're getting blocked? Also, the attacker could poison the bridge database by signing up a bunch of bridges that he's already blocked. And this means that every time Alice shows up and says, hey, can I followed your proof of work or your proof of resource or whatever, can I have a bridge address? Then we give her one that we think works, and it turns out already to be blocked in her country. And then she says, oh, shucks, I guess that Tor thing doesn't work after all, and that's it. So we'd like to have some sort of mechanism for checking these things, but in a way that isn't gameable itself. I imagine the solution will involve active and passive testing. We'll find out. So another fun point here, Tor in oppressed areas. I talk to a lot of people who say, but won't Tor use just disappear as they start to crack down? I think it might actually be the opposite. I talk to a lot of people in various countries, and their countries, I mean, Iran is cracking down quite a bit these days, but Tor use is going up. And I think the reason for that is that most people are not using Tor to point out human rights problems or to organize opposition movements. Most people are using Tor to be able to read the websites they want to read. They were able to look at their webcomics yesterday, and now they can't look at their webcomics. And there's a guy down the street who says if you just use Tor, then you can read your webcomics again. Those are most of the users. So as the government or the firewall or the ISP starts to crack down more and more, you're going to have more and more people who didn't need Tor before, but now they're using it. So I claim that the median Tor user becomes more innocent, more ordinary, rather than less as the system cracks down. I guess we'll find out. Another interesting question, internet cafes. In a lot of these countries, you don't get to show up with your own laptop and know what's on it and run your own software. You walk in, and it's an internet cafe running Windows 98, and 50 other people used that system before you, and you hope they didn't put spyware on it, and you hope the guy next to you doesn't have a security camera watching you, and so on. And that's not a very good situation for running these sorts of things. So one answer is we need to work more on bundling. In the last talk, Mike Perry talked about the slogan, "Tore up from the floor up," which is a live CD AnonymOS thing. From before. So there are a lot of different approaches. Maybe you want to show up with your USB stick and you want to pop it in and use the Firefox that it pops up and then take it out again. We can talk about that more also. How many bridges do you need to know about to stay connected? That's another big question. Let's say I've got 4 bridges, and let's say cable modem and DSL bridges rotate away and disappear from me at a certain rate. And let's say bridges also get blocked at a certain rate. And let's try to predict what those rates are and anticipate them. How many bridges do I need to know about? And how often should I fetch updates in order to always have at least one? Somebody should actually do the math. Some of that math is based on numbers we don't know how to estimate. So that's a tricky question in terms of the engineering details. Another problem, cable modems don't usually run big websites. If a lot of our bridges end up on Verizon and Comcast and stuff, then shouldn't these governments just filter all connections to Verizon and Comcast and stuff? I mean, it's not like anybody runs real websites from there, they say. And then another point we might worry about is economic pressure. Maybe Verizon will go to China and say, hey, we really want to start selling our stuff. And China will say, well, that's great, but could you get all your users to stop running Tor bridges, and then we'll talk. So that's another attack that we might want to worry about. And then another key point here, publicity attracts attention. I talk to a lot of journalists all the time who really love writing articles about the Chinese firewall and about researchers who are trying to figure out how to get around it. One of the reasons why Tor still works in China is that we haven't had any articles saying Tor project declares war on China. For all the journalists in the room, I'd really like to ask you not to write an article about that. Because the reason why we work is because we don't publicly embarrass them. We don't have the daughter of the general in China tugging on his shirt saying, Daddy, I heard about this Tor thing, and why don't we filter it? So I'd really like to talk to you as researchers and engineers and say, this is my idea, I really need some feedback on it. Please tell me where you think it's going to break. But I really don't want to talk to you as journalists because publicity at this point isn't going to help the case. Now, I'd be happy to talk to you about publicity for Tor as freedom of speech, Tor for civil liberties, Tor for military. I talk to FBI people every so often, and they say, yeah, I use Tor every day for my work, but please don't name me. So there are a lot of other fine articles, but please don't write about this one yet. And I guess the other point is by publishing, we threaten their appearance of control. It isn't that we're actually changing the situation, but they notice us more, and they have to do something because their citizens or their bosses are going to say, hey, why aren't you dealing with this thing I just read about in the Wall Street Journal? And then another piece of that, we can control the pace of the arms race. We can decide how quickly they have to put resources into breaking these different distribution strategies, and we can decide how many resources they put into them. Okay, so next steps. Technical solutions aren't going to solve the whole censorship problem. These firewalls are really acceptable socially right now. They're really successful socially. It's not like every person in Iran is saying, darn it, I wish my government would stop filtering the internet. Most of them are saying, I'm so glad my government filters the internet, otherwise I'd have to see all that horrible stuff out there. They're right, nobody wants to see that. And as long as most people in these countries are saying that, a technical solution isn't going to do it. On the other hand, there are plenty of people, hundreds of thousands of people, who really do want to be able to either get to their webcomics again, or they want to start, doing whatever they want to do to reform their government's policies or politics or whatever they're interested in. And I guess I'm sympathetic to that too. So I guess a strong technical solution is a piece of the puzzle, but isn't going to do all of it. So we have built bridges 2 days ago, I put out a release where you can set up your own bridge, you can connect to somebody else's bridge, there's a bridge authority that's running, and your bridge can publish to it, and we can aggregate a list of volunteers, people who've done that. It all still involves editing a text file. You have to go change your configuration file and add some lines to it. Eventually, we'll add a pretty button to Vidalia where you say, Tor for freedom, or I need freedom, and then it'll go add the correct lines automatically. But that'll be a step down the road. And then Tor itself needs to survive also. We hear from a lot of people, especially in Europe these days, where they're trying to push through data retention. Data retention is a big threat to security of ordinary people around the world, because it doesn't catch the bad guys. The bad guys are doing fine. They don't need any of this stuff. But the good guys, first of all, they don't have much in the way of security. That's what we're trying to provide for Tor. And second of all, do you really want to build a big database of everybody's doing everything on the internet? Isn't Amazon and Google, and aren't those guys already doing fine at building these databases? And isn't our job to make these databases less useful, or at least include less information? It's not like the government or the corporations that build these huge databases are very good at keeping them secured anyway. But anyway, that's a separate rant, and eventually we should talk more about data retention. It's one of the big things threatening the internet these days. And then finally, we need your help. If you want to run a Tor server, either as an exit node or a non-exit node, that'd be great. If you want to help out with all these various things, with advocacy or documentation or coding or tools or stuff like that, or if you happen to know anybody who needs anonymity or privacy or security or traffic analysis resistance and wants to pay us to make it better for them, I'd be happy to meet them too. Thank you.